Good afternoon, everyone. Thank you for being here today. I'm Xinliu. Today, I will introduce our work verification and redesign of OFDM Backscatter. This is joint work with my colleagues Zicheng, Wang, Yao, Pei Hao, and my advisor Ting Zhu. Firstly, I will briefly introduce the backscatter and OFDM techniques. In the last few years, backscatter has been proposed to transmit data on ambient signals, such as Wi-Fi, Bluetooth, LoRa, FM radio, and so on, by using square waves to modulate the ambient signals. The backscatter tag consumes very little energy to transmit data and also enable lots of IoT applications, such as smart homes and smart health. On the other hand, the OFDM has been widely used and become an essential element in advanced wireless communication, such as LTE and 5G. This is because OFDM can provide a more reliable and faster communication. To leverage productive OFDM communication from the surrounding OFDM devices, researchers recently proposed a general architecture of OFDM backscatter systems. In the architecture, there are two receivers. One is listening the original OFDM signal, the other is listening the backscatter signal. By connecting the two receivers to an edge device, the tag data can be decoded in the edge device. This architecture has demonstrated to be effective in supporting the smart office applications. However, we found that it requires specific OFDM receivers that can disable the phase error correction. We contacted multiple authors of these systems, and they confirmed that they need specific receivers that can disable the phase error correction. To fully review the impact of phase error correction on these systems, it is necessary to understand how these systems work. The existing OFDM backscatter system leverages the symbol level modulation technique to transmit data. For example, if the tag wants to transmit data 0, it uses square waves with a phase offset of 0 to modulate the symbols. Since there is no phase change, the backscatter symbol on the receiver side remains the same as the transmitted symbol. If the tag wants to transmit data 1, it uses square waves with a phase offset of pi to modulate the symbol. Since there is a phase inversion, the phase of the backscatter symbol on the receiver side is inverted. The symbol level modulation requires the tag to change the phase of OFDM symbols in the time domain. Therefore, it requires the tag to synchronize the square waves with the symbol stream. The existing OFDM backscatter systems use XOR decoder to decode the tag data. If the symbols on the two receivers are the same, it gets data 0. If the symbols on the two receivers are different, it gets data 1. However, in real-world scenarios, due to the changes of environment, such as temperature of oscillator and object movement, the OFDM symbols experience distortion in the air, and this causes much unwanted phase error. Therefore, the OFDM receiver is required to perform the phase error correction to eliminate the phase error on the symbols. It causes the phase offset introduced by the backscatter to be eliminated. For example, in this slide, the phase offset of SM returns to be 0. Therefore, the tag data 1 will be always mistakenly decoded as 0. To address this issue, we designed a novel OFDM backscatter called TScatter, which uses high-granularity sample-level modulation to avoid the phase offset created by a backscatter tag being eliminated by phase error correction. Here is the outline of our talk. First, let's focus on the modulation. The reason that phase offset is eliminated is that the phase offset on the pellets are the same as that on other subcarriers. Our sample level modulation can make phase offset on the pellets and the other subcarriers different. A fundamental basis for the sample level modulation is that OFDM symbols can be divided into sample level. For example, a Wi-Fi OFDM symbol includes 80 samples. When the backscatter uses square waves to modulate the phase of the symbol, it essentially uses square waves to modulate the phases of the samples. If we change the phase of each square wave according to tag data, we can embed the tag data into the OFDM samples. Here, let's recall symbol level modulation. The phase of all square waves are the same, so the symbol level modulation is a special case of sample level modulation. Next, let's talk about the demodulation. The objective of TScatter's demodulation is to decode the tag data on OFDM sample subcarriers. To achieve this objective, we need to understand how the OFDM receivers convert the backscatter samples to the subcarriers. To do so, we divide the workflow of an OFDM receiver into 3 parts and build a model for each part. Especially, TScatter is the first work that builds the pilot tracking and phase error correction models for OFDM Backscatter. If more details are needed, please refer to our paper. Since we consider the impact of phase error correction, TScatter is a more generic design. Although the demodulation is complicated, we provide a light version of TScatter. We use an example to explain the light version. In general, the existing OFDM backscatter uses multiple symbols to convey 1 bit of tag data. For example, this slide shows that tag data is conveyed by 2 symbols, and the tag was to transmit data 0110. From previous analysis, we know that symbol level modulation is a special case of sample level modulation. So we can also use symbol level modulation to make the phase offset on the pilot being different from that on other subcarriers. This is very simple. Don't synchronize the square waves with the symbol streams. After the modulation, the backscatter symbols on the receiver side are like this. The symbol S0 and S6 are modulated by the square waves with a phase of 0, so they may remain the same as the receiver side. The symbol S2, S3, and S4 are modulated by the square waves with a phase of pi, so their phases are inverted. The symbol S1 and S5 are modulated by both of square waves with a phase offset of 0 and pi. Their phase offsets on different subcarriers are different. We use X to represent their phase offset. After phase error correction, the phase offset pi is eliminated. Since the phase offsets of X on different subcarriers are different, the phase offset of X cannot be eliminated. After XOR decoder, we get the result 010010. Now we further analyze the XOR decoder results. Since we use 2 symbols to represent 1 bit tag data, we can divide the adjacent 2 decoder results into a group. In general, the tag firstly transmits a long sequence to reflect the preamble and several symbols, so the first bit of tag data can be predefined. If the decoder result is data 1, that means there is a phase change from tag data 1 to 0 or from 0 to 1. So we can define the decoder result of data 1 as an inversion sign. In the first group, there is an inversion sign. The final decoding result in the first group should be different from the predefined data. It is 1. In the second group, there is no inversion sign. The decoding result of the second group should repeat the last bit of data. It's still 1. The third group contains an inversion sign. Therefore, we can invert the last bit of data to get the final result of the third group. It's 0. Now we get all tag data correctly. Finally, we show the evaluation result. We built the hardware of TScatter. It's compatible with open source Backscatter platform. We also extensively evaluate TScatter under different modes, different modulation schemes, and different coding schemes. First, we evaluate the performance of our design by comparing our system with the 3 other state-of-the-art OFDM backscatter systems. The figure shows under similar throughput, the bit error rate of TScatter are much lower than that of other solutions. Bit error rate is reduced by a factor of 100. This is because our design takes advantage of the phase error correction, which can significantly reduce the phase error. Second, we compare TScatter performance with the light version under different OFDM modulation schemes. The left figure indicates that as the modulation level rises, so does the throughput of TScatter. This is because the higher modulation granularity with a higher density of tag data can be embedded. Finally, we evaluate our design under several different coding schemes. From the figure, we can observe that when the code rate is up to 2/3, the bit error rate is lower than 0.1%, and the throughput is as high as 5 Mbps, which provides a reliable high throughput communication. In conclusion, our contributions are as follows. Firstly, we evaluate the existing OFDM backscatter systems and redesigned the system with a novel sample level modulation technique. Potentially, this technique can be applied to LTE and 5G. Secondly, we built the first OFDM backscatter demodulation model. Finally, our system is more generic. Our empirical results show that TScatter has 2 orders of magnitude lower bit error rate than the latest OFDM backscatter systems. Thank you for your time. Now I would like to take some questions.